All right, welcome. In this explainer, we're going to tear apart the Cambridge A-Level Chemistry Paper 3. We're going to turn the most common, most frustrating exam pitfalls into your secret weapon for success. This is all about the strategy to make sure you get every single last mark.
So let's kick things off with a big question, one that's probably on your mind right now. You know your stuff. You've put in the hours in the lab. So why does this particular paper feel like it's designed to trip you up?
Well, the answer is actually pretty simple. This exam, it's less about how much chemistry you know and more about spotting the common, predictable traps they set for you. But here's the good news. Once you see them, you can't unsee them. And today we're handing you the complete map.
Okay, let's get into it. Here's our game plan. We're going to tackle the 5 critical areas where marks just seem to vanish. First, we'll decode the exam's patterns. Then, we'll dive into calculations, master those tricky graphs and techniques, get the language of chemistry just right, and finally, pull it all together to lock in that A-star grade.
First up, let's decode the exam's DNA. You know, the most important thing to realize about Paper 3 is that it's actually super predictable. You just have to know the secret rules of the game before you even start.
Now, this is really interesting. Think of these numbers as your own personal built-in alarm system during the exam. If you do a titration and your final answer is something like 45 cubic centimeters or your temperature change is only 2 degrees, these benchmarks should be screaming at you. They're your first clue that maybe, just maybe, you should double-check your work. It's an instant sanity check.
Okay, let's talk calculations. This is, let's be honest, where so many easy marks just disappear. It's often not because the chemistry is hard, but because of tiny, avoidable mistakes.
Take a look at this. You've done all the hard work for an enthalpy calculation. You've got your numbers right, and you write this down as your final answer. It looks perfect, right? But it's not. There is one tiny detail here that is fundamentally wrong and will cost you the mark. Can you spot it?
Here it is. This is the key. The reaction between a strong acid and a strong base is always exothermic. It gives off heat. And in the language of chemistry, that means the sign for delta H has to be negative. Forgetting that little minus sign is probably one of the most common ways students lose a mark, and it's so easy to fix. And here's another classic. In our beloved Q equals mc delta T, what does M actually stand for? It's the total mass of the stuff that's heating up. So if you mix 50 grams of acid and 50 grams of alkali, your M is 100 grams. Always use the total mass. It's a very easy mark to lose, but an even easier one to get right.
Okay, let's switch gears to a stoichiometry experiment. You're reacting a piece of magnesium ribbon with acid, collecting the hydrogen gas, everything's going great. But what if that shiny ribbon isn't quite as pure as you think? What about that invisible layer of oxide on the surface?
And this is such a great example of how a real-world issue can totally mess up your results. See that magnesium oxide on the surface? It reacts with the acid, sure, but it produces water, not hydrogen gas. That means the volume of gas you collect is less than you expected. So when you do the math, it looks like you had more magnesium than hydrogen, and your mole ratio gets skewed. It's a classic trap.
All right, so that's calculations. Now let's see how these ideas about precision carry over into our practical techniques and graphs. This is where your hands-on lab skills really get put to the test.
Oh, this is a classic exam question. Picture this. You rinse your pipette with distilled water, which seems clean, right? But then you fill it with your sodium hydroxide. What happens? That little bit of water dilutes your alkali. So now you have fewer moles in your flask, which means you need less acid to neutralize it. Your titer volume is too small. And when you plug that small number into your calculation, boom, your final acid concentration comes out way too high. You have to follow that chain of logic. Okay, rates of reaction graphs. Listen, if you remember one thing from this whole explainer, let it be this. You absolutely cannot, ever, just take the first 2 points from your results table and calculate the gradient. I'm serious. That is a guaranteed way to lose marks every single time.
So here's the right way to do it. Follow these steps exactly. First, draw a nice, smooth best fit curve. Then, line up your ruler and draw a perfect tangent that just kisses the curve at time 0. Now, and this is so important, pick 2 points that are far apart on your tangent line, not your data points. Use those 2 points to calculate the gradient. And for the love of chemistry, don't forget your units at the end.
Next up, qualitative analysis. In this section, being vague is your worst enemy. The exact words you choose are just as important as getting the right test tube to change color.
Let me be crystal clear about this one.
This isn't a friendly suggestion, it's an unbreakable rule. You must acidify with dilute nitric acid before you test for halides. Why? Well, think about it. If you used HCl, you're adding chloride ions yourself, instant false positive. If you used sulfuric acid, you might precipitate something else entirely. Nitric acid is the only one that stays out of the way and lets the real reaction happen. And just look at this. The examiners have a checklist, and blue is not on it. Light blue precipitate is. They don't want green. They want gray-green precipitate. And for silver bromide, that killer description is cream precipitate. It's not white, it's not yellow, it's cream. Learning these exact phrases is just free marks waiting for you to collect them.
All right, let's bring it all home. Getting that A-star isn't always about knowing more chemistry than everyone else. It's about having a mindset of extreme precision and paying attention to every single detail. This is what separates the top performers.
Think of this as your non-negotiable checklist for every question. Show all you're working. Use 3 sig figs for your final answers. And this one is huge. Burette readings must have 2 decimal places. You write 24.50, not 24.5. That 0 matters. Never forget units, always use state symbols in ionic equations, and make your graphs big and clear. These aren't just suggestions, they are the habits of A students.
So I want to leave you with this final thought. Ask yourself this. Are you just revising chemistry content, or are you training to beat the exam itself? Start thinking like a strategist. Learn to spot the traps, master the techniques, and practice the precision. That's not just how you pass, that's how you win on exam day.